Good afternoon, everyone, and welcome to Café Scientifique from all of us at SFU's Faculty of Science. My name is Suzanne Stockdale, and I work here in the Dean's Office as the Senior Director for the Faculty of Science. If you're one of our cafe regulars, thank you for joining us again, and if you're new, thanks for joining for the first time. Café Scientifique is a Faculty of Science's public seminar series where our presenters share their current scientific research and its impact on our local communities and our larger society. We typically host about 6 a year, and they're all virtual. They're also recorded, so you can view them from our website if you missed anything or would like to share the presentation with a family or friend. We'd love to hear from you, so please stay in touch. After the event, you'll get a feedback link by email, and if you're interested, you can join the mailing list to receive updates about all of our future events. I'd like to start us off in a good way by acknowledging that I am privileged to join you today from the unceded and ancestral lands of the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam peoples. We thank them for having cared for and been stewards of this land and waters since long before our time here. And we look forward to working with them in partnership as we continue to build and grow our communities together. If you don't know or if you know on whose territory you are currently on, I invite you to take a moment to reflect on this. And if you don't know whose land you're on, a great resource for more information is the website native-land.ca. There you can familiarize yourself with Indigenous peoples on whose land you work and live. So just to go over the format for the evening briefly, there will be a time for questions after the Q&A. And so you'll have an opportunity to ask questions of Joshua. Please use the raise hand function, which you'll find under the react button at the bottom of the menu, and we will unmute you so you can talk. Or you can type a question in the chat if you would prefer. We would love to see your faces, and so we invite you to turn on your cameras during the Q&A. We also ask that you please rename yourself if you haven't already done so in the display name so we know who you are. Live transcript is available for your convenience. And also just to note that, as you probably heard, we are recording this event, and we will be sharing it broadly, so just so you're aware of that. So let's get to tonight's discussion. I'm pleased to introduce Joshua Yu, a graduate student in the Department of Chemistry. Cancer is a leading cause of death worldwide and kills 1 in 4 Canadians. One powerful tool that is used to fight cancer is medical imaging. It allows doctors to non-invasively locate cancer in patients, which guide decisions for treatments. PET scans are a type of medical imaging technique that measures gamma ray radiation. As part of his research, Joshua is assembling a complex gamma ray radiation detector that he can use as a tool to research new approaches to PET scans. This new approach could possibly improve imaging quality and therefore patient outcomes. I have the pleasure of hearing Joshua talk earlier this year during 3-minute thesis competition, and I'm very much looking forward to hearing him expand on that this evening. So over to you, Joshua.
Thank you so much, Suzanne, for the warm introduction. It really is a privilege being here to share my research on such a great platform like Café Scientifique. So without further ado, let me just share my screen. All right. All right. So today I wanted to share with everyone the type of research we've been doing at the SFU Nuclear Science Laboratory. So this is a laboratory located in the Department of Chemistry here at SFU Burnaby. And the kind of research we do is everything from nuclear structure studies to building radiation detectors. And in my case, I'm focusing on research related to medical imaging. So this presentation, I'll break it up into 4 parts here. First, I want to talk about some key concepts in nuclear science just to get everyone on the same page. Then I'll talk a bit about medical imaging, and I'll talk about the 8 pi gamma ray spectrometer. So this is a radiation detector, which we put together here to do something called a 3 gamma PET scan. So the first question to ask is, what exactly is nuclear science? Well, nuclear science is a very multidisciplinary field of science. A good example of this is that many of the students or my colleagues in my research group are from the Department of Chemistry, the Department of Physics, or Engineering Science. And this branches further out even to biology, medicine, or environmental sciences. Right. And nuclear science is essentially a science focused on the study of the atomic nucleus. So its constituents, behaviors, interactions, and radiation. So what I have right here is a not to scale cartoon of an atom. And inside an atom, in the core of an atom, we have protons, which are colored here in green, and we have neutrons in blue, and together they form what's called a nucleus. And surrounding this nucleus, we have electrons, which I've colored here in red, right? And electrons, they have a electric charge of -1. Protons have an electric charge of +1, and neutrons are neutral. To give us an idea of the nuclear scale, the nucleus I just showed you in the previous slide is very small and dense. So if that atom, which I showed you, was the size of Vancouver, then the size of the nucleus would be proportionally the size of a blueberry, right? So it is that small. Over 99.9% of an atom's mass comes from its nucleus, while over 99.9% of an atom is just empty space. Now, in terms of length and energy, when we're talking about atoms, so on an atomic scale, we're usually talking in a length scale of nanometers. So a nanometer is 1/1000th of a meter. And on the nuclear scale, it's about 1 million times smaller. So we're talking femtometers, and this is 1/quadrillionth of a meter, right? And then on energy scales, we use this unit of energy called electron volts. And in an atom, we're usually talking on the scale of electron volts, whereas in a nuclear setting, nuclear science, we're usually speaking in terms of mega electron volts, which is 1 million times greater than an electron volt. Here's an example that can be applied to something more familiar to us. If you were to burn 1 gram of fuel, of coal, you would get approximately 35 kilojoules of energy. So a kilojoule is just a unit of energy. And, this is enough to boil 1 tablespoon of water. Burning 1 gram of gasoline can release 45 kilojoules of energy, enough for approximately 1.3 tablespoons of water to be boiled, right? So these first two processes are atomic processes. Now, when we move on to these nuclear processes, for example, uranium-235 fission, we're looking at 80 million kilojoules of energy being released. So that's enough for 35,500 liters of water to be boiled. And in the case of fusion, deuterium-tritium fusion, the energy released is on the order of 330 million kilojoules. So that's 146,700 liters of water that can be boiled with this amount of energy. I think a good place to start is to understand how we got here and how nuclear science came to be. And I think this begins with our human curiosity to understand the natural world around us. And you can see evidence of this all the way back to 450 BC, where we have Greek philosophers hypothesizing that the universe is made of four elements: fire, water, earth, and air, and also two fundamental forces, love and hate, right? So on the left here, you see possibly the earliest version of a periodic table of elements where elements are being described as either hot, cold, dry, or wet, right? But we fast forward about 2.5 millennia, and we have this English scientist by the name of John Dalton who introduces atomic theory to chemistry. So this is the theory on atoms. And to summarize his work in 4 points, he says that matter, which is everything that you can see, touch, taste, right? Matter is made of indivisible atoms, so these indivisible building blocks. And he also says that atoms of the same element have the same properties as opposed to atoms with different elements having different properties. He says that atoms cannot be created or destroyed, and that these atoms can be combined in certain ratios to form these chemical compounds, right? So this is what we call molecules. About 100 years later came the discovery of radioactivity. So this was by a French scientist, Henri Becquerel, and he was interested in these phosphorescent materials. So these are glow-in-the-dark materials. And he wanted to see um, what would happen if you were to take a phosphorescent material and place it on top of a photographic plate wrapped in black paper out in the sun? So a photographic plate, you can imagine like film paper, which when exposed to light or radiation will fog up after processing. And he wrapped these photographic plates in black paper with this glow-in-the-dark material on top. And the idea is that he wanted to see the sun energize this phosphorescent material and see the emissions coming from the phosphorescent material penetrate through the black paper and onto the photographic plate. So he was getting these patterns. However, one day when he was doing his experiments, the weather was overcast, meaning it was very cloudy and there was not a lot of sun out. So he left his photographic plates wrapped in black paper, along with his phosphorescent materials in a dark cabinet that day. And just by chance, the next day, he decided to process his photographic plates, and he still saw the patterns of the phosphorescent materials on the plates, despite them being stored in the dark cabinet without the sun. And so from this, he hypothesized that there was penetrating radiation coming from his uranium salts without the need for external energy. So this is the important point here. It's without the need for external energy, which is what defines, which is what is the difference between just a regular phosphorescent material and a radioactive material. Around the same time, more radioactivity research was being done by Pierre and Marie Curie. These two coined the term radioactivity, and they're also responsible for discovering polonium and radium, two radioactive atoms. They also showed that radioactivity was an intrinsic property of the atom as opposed to a property of molecules, for example. And they also paved the way for the medical and scientific applications of radioactivity, which we have today. For example, I think Marie Curie even showed that exposing a tumor to radiation can help kill it, which is important for radiation therapy, which we have today. Now, up until this time, the majority of scientists believed that the atom was the smallest building block of matter. But in 1904 came the discovery of the electron, right? So this was by J.J. Thomson, and he was doing these experiments with cathode rays. And what a cathode ray is a stream of electrons, right? And he was calculating that these streams of cathode rays could not travel as far as they do in air if the particles in the cathode rays were the size of atoms. And so from his calculations, he found that these cathode rays must be composed of particles that are about 1,000 times smaller than the atom. And so, of course, we know today that this is the electron. And from his discoveries, he came up with the plum pudding model. So for those of you who don't know what plum pudding is, it's a Christmas dessert, usually like a steamed pudding, a sweet steamed pudding with raisins in it. And his plum pudding model of the atom described the atom as this positively charged pudding or this matter, and the raisins are the electrons, so the negatively charged electrons inside the plum pudding, with this whole thing being electrically neutral. All right, not too long after came the discovery of the nucleus, and this was actually done by Ernest Rutherford, who was a former student of J.J. Thomson. And so his discovery of the nucleus actually challenges his plum pudding model. And this was done through the famous Rutherford scattering experiments, where Ernest Rutherford and his students were scattering alpha particles, which are two neutrons and two protons together, at this thin gold foil. And the scattering pattern or the trajectory of these alpha particles were showing behavior that you would not expect if the plum pudding model was true. And so he described it as if you were firing a 15-inch shell at a piece of tissue paper and it came back and hit you. And so from his Rutherford scattering experiments, he hypothesized that there must be something very small, charged, and dense in the core of the atom. This is what we know as the nucleus. Now, if we fast forward to today, we have many applications of nuclear science. On the left here, I have a picture of a small modular reactor. Uh, Nuclear science is used in the energy sector where we are taking advantage of nuclear reactions to extract heat and energy. We see nuclear science in applications of medicine. So this is a PET-CT scanner, and nuclear science, the principles of nuclear science are used to measure radiation coming off of a patient to image functions inside of the patient, right? You may have heard of carbon dating, where you can measure radiation coming off of fossils uh, to estimate how old these fossils are. And there's also applications in space where we are using principles in nuclear science to understand the origins of our universe and also things like the composition of our star. Throughout this presentation, I will be using a special notation to denote nuclei, right? So for any given element X, we will write it exactly like this, where X is the elemental symbol. We'll have A as the number of nucleons, and a nucleon is either a proton or a neutron. So A is the number of protons plus the number of neutrons. Z is the number of protons, and N is the number of neutrons. And so just as an example, fluorine-18 would be written exactly like this, how you see here. You may hear me using the word isotopes throughout this presentation. So this just means that I'm keeping the number of protons constant for an element while varying the number of neutrons and thus the number of nucleons. And sometimes you'll see me writing this as a shorthand. So for fluorine-18, the example here can be written as a shorthand. We just don't include the number of protons or the neutrons because they can just be understood from the element. So I would just write fluorine-18 as 18F. And so here's just an example of a nuclear reaction of deuterium-tritium fusion. So we have hydrogen 2 plus hydrogen 3 making hydrogen 4 plus a neutron, right? Many of you are familiar with this chart. This is the periodic table of elements. And this is a chart to describe atomic structure. It arranges elements according to their electronic levels. And these elements are arranged in groups and periods as well as regions where similar elements have similar behaviors, right? In nuclear science, we have an analogous chart. This is called the chart of nuclides. And what you're looking at is a graph where on the y-axis, you have the number of protons, and on the x-axis, you have the number of neutrons. And if you were to zoom in on this colorful blob here in the middle, you'll actually see that each of these cells is populated with a nucleus, right? And each of these cells has the elemental symbol for that nucleus. You'll also notice that it's color-coded. So for this chart of nuclides here, the nuclei colored in black are what we call stable nuclei. So these are nuclei that do not transform into another nucleus over a long period of time. Right, and then we also have these colored cells. These are what we call unstable or radioactive nuclei. And so these are the nuclei which will transform into a more stable nucleus to get to a more energetically favorable state. So here's just a simple example of radioactive decay. In radioactive decay, we start with what we call a parent nucleus, and it undergoes radioactive decay, transforming into its daughter nucleus. And in this process, the radioactive decay emits radiation, and here are just three examples. We have alpha radiation being emitted at the top, beta radiation, and also gamma radiation, which is just a photon. And here you're looking at the chart of nuclides again, but colored by the type of radioactive decay. So here in blue, we have nuclei, which are unstable and which will transform, undergoing radioactive decay through beta minus radioactive decay, which emits a beta minus radiation particle, which is just an electron. We have here colored in orange examples of nuclei which will undergo a process called beta plus decay, which emits a beta plus radiation particle, also known as a positron. Here in black, we have the stable nuclei, which do not undergo radioactive decay and they do not transform over a long period of time. And in yellow, we have some nuclei that undergo alpha decay, which emit alpha radiation, and so on. So the reason why these nuclei undergo radioactive decay is because the nucleus is in an energetically unfavorable state. And in order for the nucleus to lose energy and get to a lower energy state, it does so by emitting radiation. And the radiation that it emits carries energy away from the system. Now, the type of decay and the type of radiation it emits will depend on the number of protons, can depend on the number of protons, the number of neutrons, or the overall energy state of the parent nucleus. Of course, different types of radiation have different characteristics. So here's just some examples. Here on this infographic at the top, we see alpha radiation. So this is two protons and two neutrons together. So this is a helium nucleus. And alpha radiation is relatively massive compared to the other types of radiation. And so, in addition to being massive, it also has a +2 electric charge. And so, alpha radiation does not travel very far in matter. And what this infographic is showing is that alpha radiation can be stopped by, by something like a sheet of paper, right? Now, beta radiation, which is just an electron, is relatively less massive. It's about several thousand times less massive than an alpha particle, and it only has a -1 electric charge. So this is a more penetrating form of radiation. It can travel further in matter, and in this infographic, it's showing that it's penetrating through paper and is stopped by aluminum. Now, gamma radiation, or a photon, um, is very penetrating, which is a very important characteristic for medical imaging. But it's a massless particle; it has no charge, and so it can penetrate very long distances through matter before being stopped, typically by a very heavy element such as lead. And of course, there's the neutron itself. This is an uncharged particle, and here it's being shown being stopped by concrete. So the room you're sitting in right now has radiation passing through it. There's actually radiation everywhere you go. This is called background radiation, and background radiation can come from places like the sun, space, it can come from the earth, it can even come from the food you eat, the water you drink, right? Um, but to give you some reassurance, this background radiation is actually in very small amounts. So the annual public dose limit in Canada is about 1 millisievert. So a millisievert is a unit of radiation dose. And the typical amount of background radiation you get is about 1,000 times less. So 0.001 millisieverts, right? You know, if you're traveling across Canada on a flight, you can expect to get uh, 200 times the radiation dose that you would get in a typical year. So although this radiation is all around us, it can be it is not visible to us with our own eyes. However, we can use certain tools to see radiation, one of which being a cloud chamber. So I have a video here that's playing. And what this video is showing is a cloud chamber. It's a video of a cloud chamber, which is a glass box with a black bottom. And this glass box is filled with alcohol, about 1 centimeter of alcohol. And this entire contraption is placed over a sheet of dry ice. And as the dry ice cools the alcohol in this glass box, a layer of alcohol vapor forms on top of the surface of the alcohol. And as radiation passes through this layer of alcohol vapor, it leaves these white trails. And so all these white trails that you're seeing here are radiation events that are passing through the alcohol. And if you look closely, you notice that these white trails have different shapes. And by looking at the shapes of these white trails, you can actually tell what kind of radiation has passed through. For example, the thicker and shorter trails are alpha particles passing through, like these ones here. And the reason why they're short is because, as I mentioned before, alpha particles do not make it very far in matter before being stopped, and they're thick because there are many interactions. So the alpha particle bumps into many alcohol vapor molecules during this very short distance. Now, if you look more in this background area, you'll see a lot of these longer, wispier trails. So these trails can come from particles such as beta radiation. So these beta particles are relatively less massive and they only have a -1 charge. And so they travel relatively further in matter before being stopped. And so what they look like here are these longer, wispier trails, and they interact fewer times in a given amount of distance. One interesting fact about these cloud chambers is that in the 1920s, the cloud chamber was actually led to the discovery of the positron. So I mentioned this word before, but a positron is an antiparticle of the electron. So it has all the same characteristics as an electron, except instead of having a -1 charge, it has a +1 charge. And what they were seeing in the 1920s is that uh, when a positron passes through a cloud chamber in the same direction as an electron, under an applied electric field, the positron will curve in one direction, whereas the electron will curve in the other direction with similar radiuses and similar thicknesses in the cloud in the trail. So this gave scientists a clue of the existence of positrons. And speaking of positrons, undergo this process called positron annihilation. This is when a positron interacts with an electron and they annihilate each other into gamma rays. So this occurs through Albert Einstein's mass energy equivalence, this famous equation E equals mc squared, which basically states that energy is equal to mass multiplied by some constant. And this quantity here is a conserved quantity. And so a positron, which has a mass energy of 511 kilo electron volts, which is 1,000 electron volts, and an electron, which has a mass energy of 500 kilo electron volts, will annihilate, and the energy being released must also sum to 2 times 511 kilo electron volts. So in this case, we have an electron interacting with a positron. They annihilate, and the energy is being released in the form of gamma rays. And the energy of the gamma rays will total to 2 times 511 kilo electron volts. So for a 2 gamma annihilation, each of these gamma rays will carry 511 kilo electron volts. Sorry. So what I've showed you earlier was a cloud chamber. Now this is a great educational tool that we often bring out to in-person outreach events. just to show the public that radiation does exist all around us, but these cloud chambers are not used in the modern day to detect radiation. Instead, we have these modern detectors, which allow us to more accurately characterize the type of radiation, the energy of the radiation being detected, and also the time, accurately characterize the time it is being detected. The reason why it's so important to have these modern radiation detectors is because there are actually very few ways for us to understand how nuclei work. And by probing the radiation that comes from these nuclear processes, it gives us a way to understand what is going on inside of the nucleus. So the next question is, where is this radiation being detected? Where is this research being done? So here's an example. What you're looking at here is the Triumph 520 mega electron volt cyclotron. So Triumph is Canada's Particle Accelerator Center, and Triumph is located in Vancouver, just on the UBC campus. We work very closely with Triumph, and the image I'm showing here is inside of their 520 MeV cyclotron. So this is a device that accelerates protons to very high energies, and it can be used to do nuclear structure studies. For example, one of the members in our group is using this cyclotron along with additional instruments at Triumph to induce nuclear reactions and to measure the radiation that comes off of these nuclear reactions. And by measuring the radiation that comes off of these nuclear reactions, he can then characterize the nucleus and the type of reaction that's going on. Now, the reason why I'm showing Triumph is because without Triumph, we wouldn't have the nuclear science laboratory here at the Simon Fraser University. So this is located just in the chemistry department on the 7,000 level. And this is where I primarily work out of. So this laboratory offers various detection instrumentation. We have the ability to detect different types of radiation, such as gamma rays, charged particles, neutrons. And this facility also offers a neutron generator. So downstairs in the basement, we have a concrete bunker where we have a neutron generator. So this is a device that generates neutrons, which we can use to do nuclear reactions, conduct nuclear reactions. And the reason why this is important is because we can use these nuclear reactions to generate radioactive nuclei, which can be used for studies such as medical imaging research. All right, so that brings us to medical imaging. Now, if you were listening to Suzanne earlier when she was giving the introduction, you might already know the answer to this question, but just think in your heads, what do you think is the leading cause of death in Canada in 2023? You know, we have COVID, accidents, cancer, and heart disease. Well, if you're thinking it's cancer, then you'd be correct. In fact, 1 in 4 Canadians will die of this very deadly disease. And because it's so deadly, we have very good tools for diagnosis, one of which is medical imaging. So medical imaging is a non-invasive imaging technique that doctors can use to see inside of a patient's body. It can be split into 2 categories. We have anatomical imaging, which we use to image structures, such as bone structure or tissue, the structure of tissues, right? So that's X-ray, CT, MRI. And then we have molecular imaging, which we use to image functions. For example, SPECT and PET, which can be used to image, for example, the movement of medicine in a body. So my focus is on PET, which stands for positron emission tomography. So this is a technique used to monitor physiological functions in the body. One example of PET being used is it can be used to monitor the metabolic activity of cancerous tissue. So by monitoring this, you can pinpoint exactly where this cancerous tissue is, and you can also see how it changes over time. Now, PET scans are a very popular method of medical imaging. Approximately 2.2 million PET scans are done per year in the US alone, and this figure is only increasing. And the idea is that if we can improve this PET imaging modality, it can lead to an earlier diagnosis and higher survival rates, of course. So let's talk a bit about how a PET scan works. So before a PET scan begins, we have to prepare something called a radio tracer. So this is a positron emitting source or a positron emitting nucleus that's chemically bound to a carrier molecule. So this entire thing is called a radio tracer, and this is injected into the patient. And what the carrier molecule does is it is responsible for transporting this positron emitting nucleus or positron emitting source to your tissue of interest. In this case, it could be cancer, right? And as the radio tracers accumulate at your tissue of interest, you have increasing amounts of positrons being emitted at your tissue of interest. So what happens after a positron is emitted at your tissue of interest? Well, these positrons, they can travel millimeters in your tissue before they undergo annihilation, like I talked about earlier. So in most cases, the positron interacts with an electron and they annihilate each other, meaning they cease to exist and they are converted into two 511 kilo electron volt gamma rays, which are emitted at 180 degrees apart. So this is mass energy conserved. And in tissue, approximately 60% of positrons will undergo this process. So this process we call free annihilation. Now, the other 40% of positrons that are emitted, they will also annihilate, but through the formation of positronium. So positronium is an unstable bound state of an electron and a positron. So the electron and the positron are attracted to each other since they have opposite charge, so they're bound, but it's unstable because they will eventually annihilate each other. And it comes in two types. There's parapositronium and there's orthopositronium. Parapositronium primarily decays by the emission of two gamma rays, so they annihilate and emit two gamma rays, whereas orthopositronium will primarily decay through the annihilation of three gamma rays. However, this orthopositronium is often affected by this secondary process called pickoff, where a nearby electron in the environment will come by and pick off the positron that's on the orthopositronium and will annihilate with that positron through 2 gamma emission. As a result, only 0.5% of orthopositronium will actually get the chance to decay by the emission of 3 gamma rays. And so to summarize everything I just said, positrons will annihilate through the emission of 2 gamma rays approximately 99.5% of the time, whereas just 0.5% of the time, a positron can annihilate through the emission of 3 gamma rays. And by the way, mass energy is still conserved in the annihilation of 3 gamma rays, meaning that the sum of the energies of the 3 gamma rays will still equal 2 times 511 kilo electron volts, or 1022 kilo electron volts. And so because this 2 gamma annihilation is so much more common, traditional PET scans measure this 2 gamma positron annihilation. So how does a PET scan work? So here I have a very simplified example of a PET scanner. And what a PET scanner is essentially a ring of gamma ray detectors. So that's what I've drawn here. And inside of your PET scanner, you have your positron emitting source, or it could be your patient that has been injected with your radio tracer, which contains that positron emitting source. And as these positrons annihilate near your tissue of interest, they will emit two 511 kilo electron volt gamma rays at 180 degrees apart. Because they're 180 degrees apart, they form this straight line, which we call a line of response. And as the PET scanner, these detectors on the PET scanner continue to collect these lines of responses, you can begin to see that the intersection of these lines actually point to where the positron source, where the positrons are annihilating. And so a PET scanner measures these lines of responses and then back calculates where this source is located, where this positron source is being annihilated. And as a result, because the radio tracers are accumulating at your tissue of interest, it therefore calculates where your cancer is located. Right. And what I'm interested in is what I'm calling a 3-gamma PET scan. So this is the measurement of the 3-gamma positron annihilation as opposed to the 2-gamma positron annihilation that's measured by traditional PET scans. And in the same way, if you can measure the energies of the annihilations, the energies of the gamma rays coming from the 3-gamma annihilations, as well as their points of interaction on this PET scanner, then using laws of conservation momentum and also the conservation of mass energy, you can then back calculate where this annihilation occurred. Now, the difference between this and the 2-gamma PET scan is that in this type of calculation, you only need to measure a singular 3-gamma annihilation event to calculate where the point of annihilation occurred. Whereas in the previous example with the 2-gamma PET scan, you need to measure multiple 2-gamma positron annihilations to localize where the positron source is being emitted. So how is this relevant to PET? Well, there's this relatively new idea of positronium imaging where scientists are measuring positronium properties and forming spatial maps of them. So a tomographic map of these positronium properties. These properties can include things like lifetimes, formation probabilities, the ratio between ortho and para positronium. And these properties are important because positrons and positronium, their annihilation is sensitive to the molecular environment surrounding them. And because they're sensitive to the molecular environment, they can be used as an early biomarker of disease before functional and structural changes. Right. And the sensitivity to this molecular environment can provide complementary diagnostic information in ways that other medical imaging techniques do not. Not only that, but measuring these positronium properties through positronium imaging can also be done in parallel with PET. So it requires no additional radioactive dose to the patient. One of these properties that I'm interested in is the 3-gamma to 2-gamma annihilation ratio. So I want to measure how many 3-gamma annihilations are occurring with respect to the amount of 2-gamma annihilations that are occurring. And this has been shown to be an indicator for things like tissue porosity and hypoxia in the tissue. But in order to measure this annihilation ratio, I need to first localize where these 3-gamma annihilations are occurring. So in other words, I need to create a 3-dimensional spatial map of these 3-gamma annihilation locations, or a 3-gamma PET scan. To do this, I'm using the 8-pi gamma ray spectrometer. So this is a highly efficient gamma ray detection device that we have here in the nuclear science laboratory. And the reason why that is important is because 3-gamma positron annihilations only occur approximately 0.5% of the time in tissue. And so it is important to have a very efficient detection device to detect these rare annihilations. Here's an inside look of the 8-pi gamma ray spectrometer. So it opens up into 2 halves, which we call 2 hemispheres. And these silver geometric shapes that you see here, these are the detectors, the detector faces. And these 2 halves come together and surround this spherical sample chamber here you see on the left. This is where your radioactive sample would go into, whatever you're trying to measure. And you'll notice that these detectors would almost completely enclose this central sample chamber, meaning it has a very good solid angle coverage. That's important because good solid angle coverage means that you can measure gamma rays, which are emitted in nearly every direction. The 8-pi gamma ray spectrometer is organized into an icosahedron symmetry. So This is a platonic solid with 12 vertices and 20 faces. And at each of the vertices, you have what we call a BGO ball pentagon detector. And BGO just stands for bismuth germanium oxide, which is the material that the detector is made of. And at each of these faces of the icosahedron geometry, you have what we call a BGO ball hexagon detector. Here's a look at what these detectors look like when they're taken out of the detector array. So these are the BGO detectors. This is the pentagon detector, hexagon detector, and here are 3 hexagon detectors assembled together to form an icosahedron face, right? And so what happens here is that this detector will produce an electrical signal which we can measure when gamma ray radiation interacts with the BGO material. And so when you have your positron annihilations occurring, they annihilate emitting gamma rays. The gamma rays interact with your BGO material here, and these electronics allow it to be converted into an electrical signal, which we then measure to extract information about the radiation. So those detectors are kind of like the eyes of the operation. And then this digital data acquisition system, which we put together, this would be the brains, right? So this is what's processing these electrical signals and essentially turning it into analyzable data. So I won't go through every component here, but it's taking the electrical signals from the detectors and it's processing it into something that we can then analyze and turn into a 3-gamma PET scan. Here is what that digital data acquisition system is really measuring. So these are what we call waveforms, and these are the digital representation of how the spectrometer is responding to the gamma ray radiation. And so here is, for example, a detection of gamma ray radiation, and these waveforms are essentially what these electrical pulses look like from the detector. And by analyzing these waveforms, we can actually extract information such as the energy of the gamma ray being detected and also the time of detection. It's important to mention that the 8-pi gamma ray spectrometer is a timing device, meaning that it can precisely measure the time when the radiation is detected. The reason why this is important is because positron annihilation emits gamma rays at the same time, and you want to know which gamma rays were detected in coincidence, so at the same time, and which gamma rays were not detected in coincidence, so that you can group events together. And so the timing resolution, which I'm showing here for the 8-pi gamma ray spectrometer, we can measure to the nearest 1/100 millionth of a second. So 7.2 nanoseconds to 19.3 nanoseconds. Okay, so what we've done is we've put together this 8-pi gamma ray spectrometer at the Nuclear Science Laboratory, and then we went ahead and used it for a 3-gamma PET scan. So first we need to create our positron emitting source. So what we chose is Teflon, and Teflon is a polymer chain of C2F4, so C being carbon and F being fluorine. So this is very rich in fluorine. And the reason why we choose Teflon is because the fluorine can be activated with our neutron generator. So by bombarding the fluorine-19 inside of the Teflon, we can then get fluorine-18, which is the most commonly used PET radionuclide, right? And this fluorine-18 will undergo beta decay to oxygen-18, and in the process, it emits a positron. So this is the reaction of interest here. This fluorine-18 undergoing a radioactive decay to oxygen-18 and emitting this E+, which is the positron, which is the annihilation we're trying to measure. So we have this Teflon disk. We secure it to a lab stand in front of this neutron generator. We turn the neutron generator on, letting the neutrons bombard the Teflon disk. And what we're left with is this radioactive disk with fluorine-18 inside of the disk, which we then put inside of the 8-pi and measure the annihilations. So these annihilations are occurring with about 99.5% 2 gamma annihilations and 0.5% of the time 3 gamma annihilations. And since we're interested in the 3 gamma annihilations, we have to somehow filter the data. We have to pick out the 3 gamma annihilations from the sea of 2 gamma annihilations. And so we do this data analysis where I'm selecting for positron annihilation events with a multiplicity of 3, meaning that 3 gamma ray detections were detected in coincidence within a narrow time window. And after I select these events with multiplicity 3, they can still be contaminated with background or random detections, right? So what I do is I plot the energy sum of these multiplicity 3 annihilation events onto what we call a gamma ray spectrum. So this is the number of counts versus the energy detected. And in this case, it's the energy sum. And what we see is the characteristic 1022 kilo electron volt peak. So this indicates that mass energy is being conserved in this process. And since my events of interest are underneath this peak where mass energy is conserved, I'm only keeping the events that have 1022 kilo electron volts of an energy sum. Right. And then with these filtered events, I'm plotting them on something called a ternary energy histogram. So this is a visual representation for data with 3 parameters that sum to a constant. So here's an example of a ternary energy histogram where each axis represents the energy of your detected gamma ray. So you have gamma ray 1, gamma ray 2, and gamma ray 3, and the energies of the 3 gamma rays. And if you were to plot your events on this diagram, you'll see that it falls into 3 regions. The first region being the red region, which is an unphysical region for 3 gamma positron annihilation events. So any events that fall in this red region, we can just immediately discard. This yellow region is a region where one gamma ray is required to have an energy of 511 kilo electron volts. And so these events would come from a 2 gamma positron annihilation. And so that leaves the only possible region for events to populate for 3 gamma positron annihilation to be the green region here. So I take my data and I plot it on this ternary energy histogram after those previous filtering steps, and this is what I get. And as you can see, the majority of events fall along this triangle, which indicates that the majority of events are still contaminated by these 2 gamma positron annihilations. And what we're really interested in are the events inside of this triangle in the middle. And so what I do is I cut out all the events that I'm not interested in and only keep the events in the middle. So I'm masking the events. Now with these events, I need to establish where they occurred. So with my 8-pi gamma ray spectrometer, I created a computer-aided design drawing of where these detectors are located in space. And what I do is I assign positions to each of these detectors. And for each of these 3 gamma positron annihilation events, a vector can be drawn with respect to the origin of where these detections occurred. And if you were to sum the angles between these vectors, detector position vectors, they should, in principle, sum to 360 degrees, but because of geometric considerations, they sum to a little less than 360 degrees, as you can see by this distribution here. And so what I'm doing is I'm applying an angular filter here. I'm selecting for events that sum to 360 degrees because 3 gamma positron annihilations occur in a plane. So if these selected events, I plot them on yet another ternary histogram, this time for angle. And what I'm plotting here is the angle between detectors 1 and 2, the angles between detectors 2 and 3, and the angle between detectors 3 and 1. So the 3 detectors that were hit in the 3 gamma positron annihilation. And what you see here is that the majority of events fall around the center of this diagram, and any events that fall along this 0.5 line indicate events that occurred close to 180 degrees apart. So we don't want any of those events in our analysis because detections that occurred close to 180 degrees apart are indicative of 2-gamma positron annihilation. So we're keeping these events in the middle. And now with our final filtered subset events, we can then plot on a map where these 3-gamma positron annihilations occurred. So I use the equation which I showed earlier, the conservation of momentum here, to plot a spatial map of the 3-gamma annihilation locations. So what I've measured is a filtered subset of data where I have the energies of each of the gamma rays and also the positions where they were detected. And by numerically solving these set of equations, you can then plot where these 3-gamma annihilations occurred. So this is a 3-dimensional map. So this is an image of the radioactive Teflon disc in the center of the 8-pi gamma ray spectrometer. And it's actually easier to see the data if we project it onto each of the planes. So this is the same data set, just projected onto the XY plane, so a top view, a side view, XZ plane, and another side view, YZ plane. And you can see how these events are localized around where the disk position should be. Next, I do another 3-gamma PET scan, except I measure the Teflon disc shifted by 7.5 centimeters, and we see the corresponding shift in the observed data. So the work I presented here is actually an extension of some previous work by Kaspersky and Abuelia, who performed a 3-gamma energy-based image reconstruction, but using but only a 2-dimensional image reconstruction, right? So they only use 3 detectors on a planar setup, whereas what I'm showing here is a 3-dimensional image reconstruction and significantly more detectors, so 72 bismuth germanium oxide detectors. And because our setup is more detection efficient than the previous experiments, we see an improvement in reconstruction efficiency. So this is defined as the number of reconstructed events that we're getting divided by the expected number of 3-gamma positron annihilations. And so we see approximately a 5 order of magnitude improvement. Another important metric is the spatial resolution. So this is a measurement of the width of the distribution of the 3-gamma positron, reconstructed 3-gamma positron annihilation events, right? And this will tell you essentially the uncertainty in your measured location of your 3-gamma positron annihilation events. So I guess the question to address next is what are the next steps for this research? So at SFU, we're planning to add higher resolution detectors to our 8-pi gamma ray spectrometer, or novel scintillators with higher resolution. So for example, we have these high purity germanium detectors, which can be added onto the 8-pi gamma ray spectrometer. And here's an example of a gamma ray spectrum of a BGO detector versus a high purity germanium detector. Again, a gamma ray spectrum is just the number of counts on the y-axis versus the energy of the detected gamma ray on the x-axis. And as you can see, the high purity germanium spectrum in blue is much sharper. It has much better energy resolution than the BGO detectors. We would also like to repeat this measurement with these high resolution detectors, but with a Dorenzo phantom or some point-like sources, so that we can have a better idea of the point spread function of our 8-pi gamma ray spectrometer, or the resolution when measuring a point-like source. Right, and then moving to a clinical application, one of the greatest concerns with this measuring these 3-gamma positron annihilations is the rarity of 3-gamma positron annihilations. Like I mentioned before, they only occur approximately 0.5% of the time. And so to measure such rare events, you would need good geometric coverage of the patient. And so we have the advent of these new full body PET scanners, which can provide greater geometric efficiency. And the nice thing about this positronium imaging is that, as I mentioned before, it can be done in parallel with your regular, routine, traditional PET scan. at no additional cost to the patient, right? All it requires is the energy information of the gamma rays. No additional hardware. This can all be done in software. Okay, just to circle back and summarize, what we've done is we produced a positron emitting source of fluorine-18 by neutron irradiation at the Nuclear Science Laboratory of a Teflon disk. And what we did was we were measuring the positrons. We were measuring the emitted gamma rays from positron annihilation, which of course conserve mass energy. And we were doing this using the 8 pi gamma ray spectrometer. And using these detected gamma rays, we constructed a 3 gamma PET image for positronium imaging, which can provide complementary diagnostic information about the patient through measurement of the 3 gamma to 2 gamma annihilation ratio. Of course, this can provide earlier disease diagnosis. So, with that being said, I would like to thank all my collaborators and everyone for their attention, and I'm happy to receive any questions that anyone has. Thank you.
Thank you, Joshua, so much. That was just fascinating and provides really interesting insight into where we will be going with detections of cancer and hopefully even earlier detections so we have better outcomes. So that's fantastic. Thank you so much for that. Now, I think we're opening up the Q&A, and you're welcome to put up your hands, or you can put questions into the Q&A, and we can get going. So does anybody have any questions? Michelle, you have your hand raised. Just ask you to unmute there. You can... London, can we get Michelle to unmute? Or Michelle, can you unmute yourself? And we would love to hear from you.
Should have the permission now. It might just be loading.
Oh,
Do
there's
you hear me now?
Michelle. Yes.
Sorry about that. So I'm wondering the Teflon, how does that transfer into what would be scanning in the human body? Would it be some sort of like, yeah, I'm not sure if that's clear. If it's not, I can clarify.
Right.
Is the
So,
Teflon what supposed to be in place
right. Yeah, yeah.
of a human?
So of course, we wouldn't be measuring irradiated Teflon in a human body, but for the sake of demonstration and the need for a positron source, we decided to go with Teflon because it's relatively easily accessible, chemically inert, but also because it's a good source of fluorine. So the reason why we chose Teflon here is because it allows us to make fluorine-18, which is the most commonly used positron emission tomography radioactive nucleus, right? Now, in a human
Okay.
body, it would be
So
different.
yeah. Well,
Sorry?
I watched the Saturday morning lectures, the SFU this last Saturday, and they were talking about having sugar that has isotopes attached to it that they either inject or inject, and then the cancer cells gobble it up, and then you treat the cancer. But I'm wondering like how it would transfer from being a Teflon sample to being identifying cancer in the patient. Or maybe that was previous to your lecture. And maybe
Oh,
that's
right.
I'm
Okay.
understanding. I don't
Yeah,
have the PET scan.
I think I understand what you're trying to ask. What happens in your example is typically they use what's called a medical cyclotron. So what they're doing is they are bombarding protons at water to create fluorine-18. So they're starting with this oxygen and they're bombarding protons at it to create fluorine, which they then attach to these sugar molecules. So I believe it's called fluorine-18 FDG, and this is what they're injecting into the patient. However, we do not have access to a medical cyclotron here at the Nuclear Science Laboratory, but we still want to measure this fluorine-18 positron emission. And so there is more than one way to get fluorine-18, and one of the ways is to irradiate Teflon with neutrons. So this irradiation of Teflon would not be used in a clinical setting for producing fluorine-18 FDG, for example, or that fluorine-18 attached to that sugar that you were mentioning.
Okay, I have one more question. On slide 59, you had some measurement of 4 to 5 centimeters, and is that the approximate size of?
I'm sorry, you cut out.
Oh, is it um, my measurement of my cent?
I'm sorry, could you repeat that last part again?
So I'm wondering if Michelle's wondering if that's the
I'll
size of
skip
the
the question.
Teflon. Is
And
that, Michelle, is
uh,
that the size of the Teflon you're wondering about, the Teflon disc?
yes, yes,
Oh,
yes,
no. So what I'm
yes.
showing here is the size of the distribution of my measured 3 gamma positron annihilation points. So basically the spread of these points. And the tighter your distribution is, the better you can localize where this 3 gamma positron annihilation is occurring. So with a wide distribution, you have a larger uncertainty than with a tighter distribution. And so what I'm saying here is that my data points are spread by 4 to 5 centimeters.
So any other questions? I know I'm super curious that when you talk about the 8-pi spectrometer, what does 8-pi come from?
Yeah, that's a great question. So the name 8-pi actually originates from when it was being built back in 1985. If you imagine a unit sphere, so a sphere with a radius of 1, the surface area of the sphere is 4 pi, right? A sphere has a total solid angle or a coverage of 4 pi steradians. And so when you have detectors arranged around a full solid angle, we typically call this a 4 pi detector array. Now, when the 8 pi gamma ray spectrometer was first built in 1985, it had two 4 pi detector arrays. It had the BGO detector array and it had a high purity germanium detector array, both of which are 4 pi. And so 4 pi plus 4 pi gives us 8 pi. So that's where the name 8 pi comes from.
That's fascinating. That's fascinating. So I'm just curious. Oh, sorry, we'll let Kay, we'll unmute you so you can talk. You go ahead and ask.
Hi. Can you hear me?
Yeah, I can hear you.
Yeah. Sorry if you you may have touched this briefly during the presentation and I missed it. But the pentagon detectors and the hexagon detectors, do those have do those do different functions or are they just different shapes for geometric purposes?
They are just different shapes for geometric purposes, just so that it fits together. Yeah. They are both BGO detectors. They are just different shapes.
So I'm curious, why use fluorine 18?
There are many reasons to use fluorine 18, one of the reasons why fluorine 18 is so popular in a clinical setting is because it actually emits a positron with the lowest amount of kinetic energy compared to other common non-metallic positron emitting nuclei. For example, like carbon, nitrogen, oxygen, those all have positron emitting isotopes, but out of the non-metallic positron emitting nuclei, fluorine 18 emits a positron with the lowest kinetic energy. And the reason why this is important is because after a positron is emitted in tissue, it can travel some distance before it annihilates. And so if your positron has a high kinetic energy, it can travel further distance from the original location where it was emitted before it undergoes annihilation. And if that occurs, then your image or your spread of points becomes more distributed. You want all your annihilations occurring as close as possible to where the positrons are being emitted. So you want the positron that is emitted the lowest amount of kinetic energy.
And what are you thinking in terms of clinical, potentially moving to a clinical setting and actually using this? Do you think that's a possibility?
I certainly do think it's a possibility. I think the major hurdle right now is that the geometric efficiency, basically the efficiency of detection. As I mentioned before, these 3 gamma positron annihilations do not occur very often. They're a rare event to observe. Just 0.5% of positron annihilations will emit 3 gamma rays, whereas the rest will primarily emit 2 gamma rays. And so if this would be implemented in a clinical setting, you would likely see it in a type of PET scanner with a greater geometric coverage. For example, a full body PET scanner. And also another factor is that this PET scanner would also need energy information of the gamma ray being detected, right? To do the method that I presented here.
Right. Well, maybe one day that would be awesome to be able to
Right.
do that. It's an excellent possibility. Do we have any other questions from the audience? No? Well, thank you so much, Joshua. That was just fascinating, and it's so exciting to hear about the work that you're doing. So we've reached the end of our time today. If there have been other questions or you think of something a little bit later, please feel free to reach out by email. We'd love to hear from you. We're just so pleased, Joshua, to be inspired by the work that you're doing. It really is exciting. So thank you all for joining us this evening, and we will see you at the next Café Scientifique in November. We look forward to seeing you then. Thank you so much.